Hello and welcome to helpyourmath.com. In this video, we are going to look at the parent function graphs of logarithmic functions. And you may recall, logarithmic functions, the parent functions are of the form f of x is equal to log base b of x. And in this case, b is our base and b has to be bigger than 0, it has to be positive. And also, b cannot equal 1. So it can be any positive number except for 1. Before we get to the graphs, let's go over some key characteristics. Let's talk about the characteristics of graphs of parent functions of logarithmic functions. That is a lot. Try saying that 5 times fast, right? Okay, the parent function f of x is equal to log base b of x will have what I call a critical point at 1, 0. So a critical point, I used this term also with exponential functions to kind of describe when the graph goes from like flat, flat, flat to all of a sudden it increases much greater than it was. I called the point where that kind of separated the two sides the critical point, and it's the same thing for our logarithmic functions. What we're going to see is that these will sharply increase or sharply decrease, then all of a sudden they kind of level out. They're not actually leveling out, but they just appear to. In between that sharp increase or decrease and the leveling out, that's where we find that critical point. Why would each parent function have a critical point at 1, 0? So if we were to look at this, why is this the case? This would be f of 1. Why is f of 1 equal to 0? So this is log base. If we do, it actually doesn't matter, we can use b of x is 1. This is saying b to what power is equal to 1? And remember that b is something positive and it's not equal to 1, although that doesn't matter here. That would be b to the 0. So b to the 0 is equal to 1. With logarithmic functions, this here, the power is the x value, and the exponent is the y value or the f of x value. So when we look at logarithms, remember they're inverses of exponential functions. I will refer back to exponential functions a lot because I tend to be more comfortable with exponential functions. That makes more sense to me. So I generally revert back to that. But putting it in the context of logarithmic functions, that's what we're talking about. So any parent function will have a critical point at 1, 0. And again, what that's doing is separating the steep increase or decrease from when it kind of levels off. Logarithmic functions have a vertical asymptote. So you may recall exponential functions had a horizontal asymptote. This is the inverse function of the exponential function. So this one will have a vertical asymptote. The parent function asymptote will be at x equals 0. And we want to pick values that will create powers of the base in the argument. So I've been using base b. We want to pick values for x. So if I just write log base b of x, we want these x values to be powers of b. Powers of b. And the specific ones that we generally want this to be, and again, it's going to be a little bit weird with my base b, but we'd be looking for like, what is 1 over b squared? Or that's, b to the negative 2. 1 over b, just 1. We would like b, and we would like b squared. So we want to know those values because that's going to be our inputs. The powers will be the inputs. One more thing before we look at an example. I know you're on the edge of your seat right now. Let's compare exponential function to its inverse, which is the logarithmic function. So let's just do the example. We'll just use 2, base 2. So our exponential function, this is going to be exponential, would be of the form, and again, I'm just using b as 2. F of x is equal to 2 to the x. So this one, we want to set this up. We know that this is a parent function, so it has a critical point at 0, 1, but we'll get to that. We want to choose, for this we can choose any values we'd like. I suggest going around that critical point. I said the critical point was at 0, 1. I would use negative 2, negative 1, 0, 1, and 2, right? We can use those 5 numbers. They're nice. We're going to get a nice contrast of the sharp increase and the steady kind of gently rising. So negative 2 for x, this would be 2 to the negative 2. That's 1 over 2 squared. This is going to be 1/4. 2 to the negative 1, that's the reciprocal of 2. That's going to be 1/2. 2 to the 0 is 1. That's our critical point. I'm just going to put a little asterisk by it. 2 to the 1 is going to be 2, and 2 squared is 4. So if I graph this, the one thing I'm missing that I haven't mentioned yet is the horizontal asymptote. So this exponential function has a horizontal asymptote at y equals 0. So let's start with that. There's that gorgeous horizontal asymptote. Now let's graph these points. So -2¼ will be like just barely above that. -1½ will be there. There's the critical point. So you can see these are, pretty close together. Now they're going to start getting further and further apart. We have 1, 2, 2, 4. And this graph is going to look like this. The next point would be 3, 8. So I'll try to hit that. Okay, so there's the exponential function. F of x is equal to 2 to the x. Now let's look at the logarithmic function. So the inverse of this exponential function would be the logarithmic function. F of x is equal to log base 2 of x. This is what we'd be looking at. And we actually know some values that we want to use for the table. In fact, we know them all because they're just going to be the inverses of our exponential. But let's solve these differently. So the way we want to think about exponential functions is we want to focus on the argument. And we want this argument to be the results of powers of 2, of raising 2 to different powers. So that's where we really want to be comfortable with the y values here, because this is going to be our x values for that logarithmic function. So what I know is that I want that argument to be, one of them to be 2 to the -2 or 1/4. That's what I want that one value to be, so I have a good sense of what I'm looking at. I want another value to be 2 to the -1 or 1/2. I want my critical point, which is going to be 2 to the 0, which is going to give me 1. I want 2 to the first 2, and 2 squared, which would be 4. So again, you can see the inverse here taking place because these were the y values of that exponential function. Those are going to be the x values for the logarithmic function. Now, what are the corresponding y values here? Well, you guessed it, they're the x values from the exponential. Plugging in 1/4 to log base 2 of x, this would be log base 2 of 1/4. This is saying 2 raised to what power gives me 1/4? And that would be -2. Next, we want to figure out 1/2. We have log base 2 of 1/2. What this expression says is 2 to what power would give me 1/2? It would be 2 to the -1. So this would be -1. Here we have that critical point. We have 2 to what power would give me 1? That would be 0. So what I'm doing here, just to re-emphasize, I'm saying 2 to what? This is my y right here. This is the y value. It's like in the problem of the exponential. 2 to what power gives me an output of 1? That would be 2 to the 0. And then we still have log base 2 of 2. So this is saying 2 to what power gives me a result of 2? That would be 2 to the first. And last but not least, log base 2 of 4. 2 raised to what power would give me 4? That would be 2 to the second. Do you know what the next ordered pair would be for this? Well, the x would be 8 and f of x would be 3 because 8 is the result of raising 2 to the third power. So if you want to put it in exponential form, you can start with the exponential form and then just switch the x and y's. That works. But it's good to try to think in logarithmic form because when there are transformations, we're going to want to be able to use the logarithmic form. Okay, so what's the graph of my logarithmic? Well, one thing I want to start with, the logarithmic function is going to have a vertical asymptote. This is a parent function, so the vertical asymptote will be at x equals 0. So I want to start with that. There it is, gorgeous. And now let's graph these points. So 1/4, -2. So the entire logarithmic function graph is going to be to the right of that purple asymptote. We have 1/4, -2, that's going to be like right here. 1/2, -1 will be here. 1, 0, there's the critical point. So you can see this is sharply increasing and now it's kind of going to flatten out. 2, 1 is here, 4, 2 is here, and I said the next one would be 8, 3, which would be there. So very carefully, I'm going to do my best here. All right, so there's the logarithmic. This one is f of x is equal to log base 2 of x. You can see it's the inverse of that exponential. To make it really clear, remember that a function and its inverse are symmetric about the line y equals x. So you can kind of see the symmetry there with these logarithmic functions. All right, we're going to cut away from the exponential and focus on the logarithmic. Let's look at our first example of just graphing a log function. So what do we remember about parent functions? We know that we're going to have a vertical asymptote at x is equal to 0, and we know we're going to have a critical point at 1, 0. So Beyond that, we want to kind of build a table of values around, notice what we have here is base 4. So what you might want to do is just set up base 4 so that we have an idea of what we want to use. So let's do exponent and answer. So exponent, we would raise 4. Remember what values we kind of want to use for the exponent, like 4 to the negative 2, 4 to the negative 1, 4 to the 0, 4 to the 1, and 4 to the 2. 4 to the negative 2, that would be 1 over 4 squared, that would be 1 over 16. 4 to the negative 1 would be 1 over 4. 4 to the 0 is 1. 4 to the 1 is 4. 4 squared is 16. Okay, so we want to kind of work with those powers, the powers being the where I wrote answer, to help us figure out what we want to plug in for x. So when we set up our table of values, one thing we know for sure, sorry about my x, that's weird looking. One thing we know for sure is that 1, 0 should be in the middle. So we want 2 values before 1, 0 and 2 values after at least. Now, what values do we want to plug in before we get to 1? Remember what we want x to be? We want these to be actual powers of 4. So what were the powers of 4 that we had? They're at this list here. So we want to plug in 1/16. What happens when we plug in 1/16? This is log base 4 of 1/16. So this is saying, what this means is 4 to what power is equal to 1/16. And what power was that? That was -2. So this would be -2. What's the next power of 4? Right here, 1/4. And this is asking 4 raised to what power is 1/4. So 4 to what is equal to 1/4? That would be 4 to the -1. We could double check our critical point, but I won't just for time's sake. Okay, what do we want to plug in next? What's the next power of 4? The next power of 4 is 4. And so this is saying log base 4 of 4 is equal to what? To give us our y value, 4 raised to what power gives me 4? That would be 4 raised to the first power. So I put the exponents as the y's and the actual powers as the x's. And the last power of 4 would be, that we're going to look at, is 16. And this is saying log base 4, 4 raised to what power gives me 16? That is 4 to the second power. Okay, so let's take all this information and build our graph. First, let's start with that vertical asymptote at x equals 0. So that's going to be a vertical line here. This vertical line is not part of the graph. It's just helping us guide what the graph gets closer and closer and closer to as the inputs get closer and closer and closer to 0. So now we have 1/16 that's barely off the vertical asymptote. -2 is going to be right here. 1/4 -1 is going to be also really close to that vertical asymptote. This thing wants to keep ending the show on me. Don't end the show. 1, 0 is going to be right here. That's why I'm making these dots really small, because otherwise that pops up. 4, 1 is here. And then I can't even fit this one. 16, it's going to be like over here somewhere. So you can see this sharply increases and then it levels out here. And that would be our graph of log base 4 of x. One more example for our parent functions. Let's look at when we have a base that is a fraction, that is in between 0 and 1. Let's look at one more example of our parent functions. This time, let's look at one that has a unit fraction as our base. What is a unit fraction? A unit fraction is when we have a fraction with a numerator of 1. So 1/3 is a unit fraction. Now, you might be freaking out like, wait a minute, I didn't sign up to have bases that are fractions. But remember, think about this in the exponential form. So in exponential form, this would be saying 1/3 to the f of x is equal to x. And you might be saying, okay, cool, that doesn't help. But what if we took that 1/3 and rewrote it as 3 to the negative f of x? So when we're talking about a base of 1/3, we can focus on the powers of 3 because those are related to the powers of 1/3, since 1/3 and 3 have a special power relationship with each other. So we can kind of focus on that, and then it's hopefully a little bit less scary. So let's do the same thing we did last time. First, let's talk about this vertical asymptote. This is a parent function, so the vertical asymptote is going to be located at x equals 0. And we have a critical point. The critical point is going to be located at 1, 0. Now what we want to do is we want to figure out powers of 1/3. we don't have to use 1/3, but it's okay. Don't let this scare you. We can just do the exponents and the answers, and then hopefully this will be a little bit less scary. So remember what we want to use for our exponents: -2, -1, 0, 1, and 2. This would be 1/3 to the -2. This is saying, well, the negative is actually going to flip it over. We're going to get 3 squared, which is 9. Hey, 1/3 to the -2 is a nice number 9. How about 1/3 to the -1? Well, that's the reciprocal of 1/3, which is 3. 1/3 to the 0, that's our critical point, that's going to be 1. 1/3 to the first is going to be 1/3. And 1/3 squared would be 1 squared over, I'm going to put that in parentheses, over 3 squared, which would be 1/9. Okay, so remember, we want to use these as our x values now. These are going to be our x values for our logarithmic function. And the powers that we see are going to end up being our y values, or our f of x values. So these here are some of the powers of 3 that we want to use. So remember, these x values, these are the powers of 3. Or in this case, sorry, 1/3. Again, they're super related, so it's okay that I am saying 3 instead of 1/3. We just want to make sure that I'm using 1/3 when we create my table of values. So my table of values here, we have x and f of x. And we want to use the powers of 1/3. So 1 power of 1/3 is 9. And how do we get 9? Let's see, this is log base 1/3 of 9. So 1/3 raised to what power gives me 9? That would be 1/3 to the -2. So it would take the -2 would be our y value. Next, we want the next power of 1/3 would be 3. And this would be log base 1/3 of 3. So what would I have to raise 1/3 to get the answer to be 3? That would be to the -1, right? That's that reciprocal. Next should be our critical point. This should be 1 and 0. We can double check that. Log base 1/3 of 1. So 1/3 raised to what power gives me 1? Yes, that would be 0. Then we want 1/3. 1/3 raised to what power gives me 1/3? That would be 1/3 to the 1/3 power. So my y value here would be 1/3. And lastly, 1/9 is our last power that we're going to look at. Log base 1/3 of 1/9. So what would I have to raise 1/3 to get to 1/9? That would be 2. So again, this should look like the opposite of an exponential function, because that's exactly what it is. It's an inverse of an exponential function. Now we're ready to graph. We have a vertical asymptote at x equals 0. So the entire graph is going to be to the right of the y-axis. We have a critical point at 1, 0. And we can graph these other points. So 9, -2 is down here. 3, -1 is right here. 1, 0 I already graphed. 1/3, 1. So 1/3 and 1 would be like right here. And 1/9, 2 would be up here. So you can see this one's like the opposite of the log base 2. This one very sharply goes down, and then it kind of flattens out, but it's still going down. It will be going down the entire, for the entire domain. So I'm going to try this the best I can. This one's a little bit harder for me. Going down, hitting those points, and then it kind of flattens out. And that would be our logarithmic function. So when we have log base b, where b is bigger than 1, we're going to see something like this, where it kind of goes up quickly and then it kind of flattens out. If we have log base b, where b is in between 0 and 1, we see that it comes down real quick and then it kind of flattens out, but it's going down the whole time. These have been examples of graphing parent functions for logarithmic functions. Thank you for stopping by.